In your assignment this week, you analyzed two key decisions from World War II. Eisenhower's decision to go into Normandy on June 6th or to delay, and Admiral Nagumo's decision as to whether to prepare his aircraft for an attack on Midway or to prepare his planes for an attack by the American fleet. One decision worked out well, the other not so much. Let's analyze these two situations based on the decision theory models presented to you in this lesson. As you recall, we described three general venues for making decisions: under conditions of certainty, under conditions of risk, and under conditions of uncertainty. Under conditions of certainty, all relevant information is known. There's one dominant or best outcome or set of outcomes. You have a finite number of decision strategies, and critically, all states of nature are known. That is, you can predict the possible conditions that may exist after your decision has been made. That was clearly not the case for Colonel Stagg, General Eisenhower's weather forecaster, or for Admiral Nagumo. Admiral Nagumo's decision was a great example of game theory. That is, the outcome or states of nature that would exist after his decision would be affected by the action of the American admirals, Fletcher and Spruance, and responsible to his initial decision. His situation might best be described as, if I do this, they do that. If they do that, then I, and so on and so forth. And the best model to solve this dilemma would be a decision tree. But I want to focus now on General Eisenhower's decision, which was, to a degree, simpler. I've developed a very simple decision table that tries to reflect the situation that he faced. The states of nature that he faced was whether the weather would be clear or rainy the day he launched the invasion. The German response didn't really affect the states of nature, although they certainly affected the potential outcomes. Ike saw the outcomes as shown in the table here. If I launch and the weather is bad, that's the worst possible outcome. If I launch and the weather is good, that's the best outcome. If I don't launch the invasion and the weather is bad, then I made a correct decision and we can go later. No harm, no foul. If I don't launch and the weather is good, then there'll be a lot of second guessing by the British, by General Marshall, by the President, and by the soldiers. It will, in fact, be a morale problem for the Army. Worse than that, we might lose the element of surprise. What to do? What to do? For decision-making under risk, it's better if we use quantitative rather than qualitative measures. Initially, let's assume each state of nature has a 50-50 chance of occurring, and the outcomes can be measured as shown here. We can do some very simple expected value calculations and make our decision. Under this situation, then, the clear decision is to go. However, all depends on your probabilities and on your evaluation of outcomes. Different assumptions as to probabilities, different assumptions as to outcomes leads to different conclusions. Assume, for example, 75-25, and the outcomes indicated here, then clearly we don't go. The lesson, test those assumptions and be careful how you calculate the resulting values under the various states of nature. Now let's look at decision-making under conditions of uncertainty. Given the same initial evaluations of results, had Eisenhower been operating under a maxi-max strategy, he would select the strategy with the best of the possible outcomes. Clearly, he would go. If, on the other hand, he'd been operating under maxi-min, he would have elected the strategy with the least bad of the possible outcomes. While not going may be bad if the weather clears, it is not as bad as going if the rains continue. Now let's look at the decisions under Savage's mini-max approach. If you'll recall, we subtract the value in each cell in a column from the largest value in that same column. This results in what we call a regret table. Then we select the minimum of these regrets. While we can do it with qualitative measures, it's far easier to illustrate with numerical values. Let's use the original values we used in discussing decision-making under conditions of risk. Notice, though, under conditions of uncertainty, we ignore the probabilities of each state of nature. First, we determine the best outcome in each column or in each state of nature. As indicated here, under rain, the best outcome is 0. Under clear conditions, the best outcome is plus 100. We identify the maximum regret for each strategy and select the strategy with the least of these maximum regrets. Under the go strategy, the maximum regret is 100. Under stay, it is 150. The strategy with the least maximum regret is the strategy to launch. To go through this again, first we determine the best outcome under each state of nature. Then we subtract each outcome in a column from the best outcome under that state of nature. We call each of these values the regret that we didn't choose a different strategy. Finally, we find the strategy with the least of these regrets. But remember, the best strategy depends on the values you assign to the outcomes. Different weights, different conclusions. If we select the same values we used to illustrate this point under conditions of risk, then the best strategy is to not go. For those of you that would like to play with these concepts a bit more, I've prepared and attached an Excel table to illustrate the decision models we've just discussed. As you will notice on the first tab under Entry, let me back up. Under the first tab called the Entry tab, you will install the values that you select for the intersection of the strategy and the state of nature. Under the second tab called Risk, you'll assign probabilities. You don't need to assign these probabilities under the conditions of uncertainty. What I've indicated in yellow, the cells I've indicated in yellow are the ones where you're to make adjustments. The formulas that I have will make the other necessary adjustments for you. For example, if I change 75 to 50, it changes 25 to 50, so that we always add up to 100%. Let me change it back though. Under the this situation, you can clearly see that S2, strategy 2, has the higher earned value, being a negative number. So clearly S2 is the way to go. I call that earned value. I should have called that, of course, expected value. Under maxi-max, we select the strategy with the best possible outcome, and that's S1 with a possible outcome of 50. Under the maxi-min, we select the strategy with the least bad outcome, and that clearly is S2. And under mini-max, again, we're minimizing our regret and also end up with a strategy under these conditions that precludes us from going. Okay? If you have any questions, be sure to let me know. And with that, good evening. I hope you've enjoyed this somewhat different approach to teaching decision theory.